Well, it's a great pleasure for me to introduce André Neves, who is going to talk to us about another blockbuster result of Fernando Marques on the existence of minimal hypersurfaces.
Okay. So I want to thank the organizers for inviting me to give a talk on Geometry Fest. Surely I'm very happy. So the thing I'll talk about is joint work with Fernando Marques, and the talk will be like this. So for the first 20 minutes, I'll motivate the problem, and I'll do a little statistical survey of the results proven. And then, because people have been doing a lot of mathematics, like Robert, they also use the board. So then I'll use the board a bit to do, some computation so that the whole thing doesn't look totally flaky. And then, if I have time, in the end, I'll state some conjectures about asymptotic behavior of minimal surface or things like that. So let me start with a guiding question. So I call this Poincaré's second best question. And the question is, does every two-sphere has a closed geodesic? And the reason why this is such a good question, it's because geodesics, they have 2 points of view. So on one hand, they can be seen as solutions to Hamiltonian flow. And then the question becomes, do solutions to Hamiltonian flows have periodic orbits? Okay, and there's a large part of mathematics, dynamical systems, or symplectic geometry, which was developed where the idea was to answer, when do Hamiltonian flows have periodic orbits? The second point of view is that geodesics, they are critical points for the length functional, and then the question becomes, do functionals always have critical points or not? And of course, if we replace a two-sphere by some Riemann surface of positive genus, then the answer becomes trivial, because as soon as the ambient manifold has topology, you can pick a non-trivial curve, a curve which you can automotopicate to 0. You pick that curve, you can minimize length in the homotopy class, and you produce a closed geodesic. So the question is more interesting when there is no apparent reason why the manifold will have a geodesic, but will still have one. So the first result, this was due to Birkhoff in 1917, and his motivation was to answer Poincaré's question. And he did show that every metric you put on a two-sphere admits a closed geodesic. And almost as good as the statement was the way you used to prove this, because the method they used to prove this, I'll talk more about this later. It's called, I think this was the first application of Minimax methods in geometry. And so the method they used to prove this then turned out to be incredibly influential in the field. So this is a good answer with an even better proof. And then some years later, Lucinic and Schnittman, they show that actually, you can do better than a closed geodesic, and every metric on a two-sphere actually admits 3 distinct simple closed geodesics. So simple means that they have no self-intersections there. And one of the great things about this result is that it's optimal on an ellipsoid. So for instance, if we take a sphere and if you shake it a bit to become an ellipsoid, but if you do it in a way that the principal axes always have different lengths, then you can put this in a way that this ellipsoid will admit exactly 3 simple closed geodesics and no more than that. So in this case we have this one here, we have that one there too, and we also have that one. And every other geodesic has to have intersection. So this ellipsoid has a lot more geodesics, but they will intersect badly, right, as the index goes to infinity. Okay, and this is again a good instance of, as interesting as the result was the method he used to do it, because in doing that, they came up with what's now known the Lucinic-Schnittman category, but also in the analysis part, this led to a big development. So maybe I should say this. So the result was a considerably number of years ahead the technical expertise we had to prove it, namely the fact that the simple here, it's a subtle issue, to make sure that the geodesics have no self-intersection, and also to make sure that we are not getting just the same geodesic, but just traveled once, twice, or 3 times. That's also a subtle issue. And many differential geometries work on the subject, to make sure one could give total solid proof of this theorem. And this had worked by Klingberg, Baumann, Yost, Taimanov, and then Grayson. Grayson, he had a crucial contribution here because, as Robert mentioned in the previous talk, he showed that the gradient flow for the length functional, which is a curve shortening flow, if we are on a surface, either exists for all time and converges to a simple closed geodesic, or if not, it just converges to a point in a round way. And so, using the fact that the gradient flow for the length functional has the best possible behavior, then one can indeed give a very conceptually easy but also understandable proof of the theorem that every metric on the two-sphere has exactly 3 geodesics. So maybe I just say that most of you know, but let me just say, why is the number 3 there? So the number is 3 because the set of all great circles in S2 is the set of all unoriented great circles in S2 is homomorphic to RP2, and every function you put on RP2 has at least 3 critical points. A way of saying this is that the lucinic schnittman number of RP2 is 3, and so that's why you have 3 there. And now the geodesics on the surface case, this was culminated in '92 by work of Franks and Begert, and they show that any metric on the two-sphere actually has an infinite number of closed geodesics. Now, there's a curious aspect of the proof is that the proof is neither purely variational, not purely dynamical. So Franks works in dynamical system, and so the way the proof works is you try to find a closed periodic orbital Hamiltonian flow, and in the cases where that does not work, which is called trapping, then you use variational theory to make sure that in the cases where the Hamiltonian flow approach does not work, then the variational theory kicks in and you still get an infinite number of closed geodesics. So one way of keep progressing on the story here is to notice that just like geodesics are critical points for the length functional, one could consider likewise critical points for the area functional. And these are called minimal surface or minimal hypersurfaces if I am code dimension 1. And so this would be the fixed points for the flow, for the mean curvature flow that Robert spoke in the morning. And I should say that the minimal surface in R3 at least is a very old topic, which older than differential geometry by like 100 years. So the first study of minimal surface in R3 was due to Lagrange, and that's about like 250 years ago. So the minimal surface in R3 is a highly classical topic, and then if you're doing geometry, it's natural to look for minimal surface on a compact manifold, and the first thing you ask yourself is, well, do they even exist or not? And so here there was a first important result of Lawson, where it showed that on the round 3 sphere, you have infinitely many minimal surface. So more precisely, if you pick any genus G surface, you can embed that into S3 as a minimal embedded surface. Of course, the philosophy here is the same as in the previous slides, that we are interested in ambient manifolds where there is no apparent reason why you should have a minimal surface. Of course, if in your ambient manifold you can find a surface which is non-homologically trivial, you minimize error in your homology class and you're going to get a minimal surface. So the 3-sphere is interesting because the topology is trivial, and it still has an infinite number of them. Then people use this technique to also construct infinite number of minimal surface on flat tori or on S2 cross S1 or on H cross R on many homogeneous spaces. Then Pitts in '81 And then Shane-Simon 1 year later, because to improve the regularity theory. So Pitts, he showed that every compact manifold always admits an embedded minimal hypersurface, which is smooth outside of codimension 7. And again here, just like in the Burkhoff previous result, the result is nice, but the method of proof is even nicer, because to prove this, Pitts and his advisor Almgren, they had to develop the old Minimax theory for the space of hypersurface in a given manifold, which was what Burkhoff did, but Burkhoff was just looking for the space of curves on an S2. And so no, this is an absolutely monumental work. Shane-Simon is there because Pitts could only get the regularity up to dimension 5, and then Shane-Simon improved on that. Then around the same year, Sachs and Uhlenbeck, they showed that if you take a manifold where the kth homomorphic group is non-zero, where k is greater or equal than 2, then you can always find a branch minimal immersed sphere. So you cannot guarantee the sphere will be embedded, nor you can guarantee that you will not have branch points. So the Jacobian can vanish at some points. This condition is absolutely crucial because, for instance, if you take a compact hyperbolic three-manifold, then pi1 is non-zero, but all the other homomorphic groups vanish. And you can have no branch minimal immersed sphere on a compact hyperbolic three-manifold.
Two-sphere, right?
That's right, a two-sphere. That's right, it's a two-sphere. So the codimension is high. Again, in doing this, in improving this nice result, in doing this, Sachs and Uhlenbeck, they actually developed a lot the theory for the existence of harmonic maps on a surface, and that has had a huge impact in the way the harmonic map theory has progressed. Then Simon Smith, 1 year later, so this is Smith was a student of Lee and Simon there. They show that if the ambient manifold is a three-sphere, then you can actually find a smooth embedded minimal sphere there, because from the results of Pitts, you have no idea what the topology of the minimal hypersurface is. So the way that Simon and Smith did this was, so it's again a min-max technique, but they don't do min-max on the space of whole surface in the three-sphere. They only do min-max on the space of all embedded spheres on the three-sphere. And it's actually a great tour de force to make sure that you can just do min-max on this smaller space. You can still prove regularity, and you can make sure that the limit will be a sphere. Then so some years later, Yost, he generalized the lucinic schnittman theorem, and he showed that on any three-sphere, you can actually put, you can actually find 4 distinct minimal embedded spheres. There's always a disclaimer I do when I state these results, is that I'm not 100% comfortable with the proof there. A crucial aspect in proving these things, you want to do min-max theory on some big space, that's okay, but you always want to exclude the fact that you get one minimal sphere, then you think you're getting the second minimal sphere you think is different, but it could be just the first one with multiplicity. And the third minimal sphere could be the first one with just multiplicity 3. So they will look like different critical points, but they are not, it's just one with multiplicity. So ruling these phenomena out for curves on the two-sphere, that requires Grayson curve shortening flow. So it's a highly subtle and technical issue here. Then White, in 91, he showed that if you look at three spheres with positive Ricci curvature, then actually he showed that you can always find 2 minimal embedded spheres. But more interesting, he showed that you can always find 1 minimal embedded torus on a positive Ricci curvature 3-sphere. And then he made this conjecture, which I find beautiful, is that any metric you put on the 3-sphere, you can always find 5 minimal embedded tori. So The 5 there, it's for the same reason that lucinic schnittman F3. So the way to get the right number is the following. So you look at the space of all minimal embedded tori on the round tree-sphere. That's the space of all Clifford tori, and that's without orientation. That's RP2 cross RP2. Okay, and then you ask, what is the lucinic schnittman number of RP2 cross RP2? In other words, if you pick what is the least number of critical points that any function will have on RP2 cross RP2, and that's exactly 5, and so you conjecture that.
What about the Lawson conjecture on the round tree-sphere?
So that's actually an interesting point. Thank you. So Brian White, this is actually one thing I find beautiful of his paper is that he proved this using a degree mapping argument, using a deformation theory, without knowing that the Clifford torus was the unique minimal embedded tori on RP3. So actually has a very clever argument where he wants to compute the degree of a map, but of course he doesn't know whether the Clifford tori is unique. So what he does is he goes to a length space where the fundamental group has very high order, and he says, well, the degree should be the same. And if you have lots of symmetries, you show that the Clifford tori is the unique one, and then he computed this. And when he made this conjecture, he didn't know that the Lawson was he didn't know that the Clifford torus was the unique minimal embedded surface. Now, of course, on the round tree-sphere, you have infinitely many embedded minimal tori, right? You pick the Clifford torus, just apply ambient isometries, you can have infinitely many of them, right? So, but if you bump it a bit, if you do a 4-dimensional ellipsoid, you should have, actually you should have 9. But you know, if you don't do a generic perturbation and still get an ellipsoid, then you would get maybe 5. Okay. Okay.
Is it known whether 5 is optimal? Is there an example where you...
Okay, so Brian White showed that small perturbations of the round tree-sphere always have, for sure, 5. Now, it's not known whether you could have a minimal embedded tree-sphere, a metric tree-sphere with only 4 minimal embedded. So no, it's not known whether it's optimal. It's known that for small perturbations, it's optimal of the round metric. In general, it's not known. It's yeah. You would expect to be optimal. You would expect it to be optimal. Just the same way that here, for minimal embedded spheres on the round tree-sphere, that's optimal. That's proven by Brian White. Okay. Okay. So having gone through this, let me state the result. I will sketch the proof. So I think motivated by all these existence theorems and by this question of Poincaré and also the geodesic case, Yao, he conjectured, so this was actually the first conjecture on the minimal surface section of his book. He conjectured that every compact tree manifold should have an infinite number of immersed minimal surface. Okay, I guess his motivation was by what was happening on closed geodesics on S2. Okay, and so the result I'll talk about is my joint work with Fernando, and we show the following. So assume the ambient manifold has dimension between 3 and 7. And we also assume that the ambient manifold has positive Ricci curvature. Then in this case, the manifold admits an infinite number of distinct, smooth, embedded minimal hypersurface. So one consequence is that when n equals 3, we answer Yao conjecture assuming the metric has positive, the manifold has positive Ricci curvature. Curiously, in the opposite case, in the farthest possible case from positive Ricci curvature, which is hyperbolic tree manifold, then 2 years ago, Kahn and Markovich, they showed that on every compact tree manifold, you can find incompressible surface of arbitrarily high genus. Actually, they counted how many. They gave a lower bound on how many you can get. And now each time you are on a tree manifold and you have an incompressible surface, you can just minimize energy in that homotopy class, and you're going to get an immersed minimal surface. So it follows from Kahn-Markovich that every compact hyperbolic tree manifold has an infinite number of immersed minimal surface. Okay, it would be great to remove immersed by embedded there. But then you can probably not do it with incompressible ones, because if you have incompressible with very high genus, then they have to badly intersect themselves, right? Okay. And Nicolas Capillas, he outlined an approach to this theorem still on when it's positive ricci curvature and for three manifolds. And his approach, so our proof is by Minimax methods, which I will describe in a second. Capillas' approach is dramatically different, and I will explain now how it is. So Capillas' idea is the following. So you pick any three manifold with positive ricci, you know for sure it has one minimal embedded a surface. Okay. Now that minimal embedded surface has to be unstable, because under positive ricci, every minimal surface is unstable. Okay. So now if it's unstable, you can move it a bit to decrease the area to one side, move it a tiny bit to decrease the area to the other side, and then his idea would be to do the doubling construction, which is to glue many tiny Lawler necks between these two surfaces. Okay? And so to obtain a minimal surface, which would look like these two parallel surfaces very close to each other, but just with necks. This is called the doubling method. Another approach he also did is using the fact that if you have positive ricci by the theorem of Ryan-White, you always have two minimal embedded spheres, right? And under generic conditions, these two minimal embedded spheres, they should intersect on nice smooth curves. And then his idea is to desingularize the intersection and put many necks around that locally would look like what's called the Shirk surface, and so to obtain a high genus surface which would approach these two intersecting minimal spheres. And of course, then you can make the genus as large as you want, and you get infinitely many. So
Andre, in the common approach there, the incompressible surfaces are or are not embedded?
I doubt they will be. I don't know, but I would be surprised if they can be embedded. You know, the hyperbolic three manifold is fixed, then you make the genus goes to infinity. I would expect that as the genus gets very high, that they have to have lots of self-intersections.
Injective on the
That's right. That's the only thing. No. Yeah, the map will be injective in the fundamental. Yeah, I don't think, if the immediate positive is fixed, I don't think we have space to make compressible. So I don't think you can get embedded there. So they're all stable. I don't think these minimal surfaces, they are all stable, meaning they are local minimums for the area functional. I don't think you can get embedded with all of them being locally stable. The index should go to infinity. But, Okay, so now what I'm going to do is, so I did the historical part, so now I'm going to briefly sketch the proof of the theorem, and then if time permits, I believe I'll have time, in the last 10 minutes, I'll just go through some conjectures Fernando and I have regarding the behavior of these infinitely many minimal embedded surface. Okay, so let's see. Can everyone see if I just write here? Okay, it's not too dark, right? Okay. Okay, so the method we use, this is called Minimax theory. Okay, so let me give a crash course on that. So Minimax theory is just, you want to do Morse theory on some large space. Okay, so the setup is, I have some compact Riemannian manifold. And I look at the space. So this is the space of all unoriented hypersurface in my manifold. Unoriented hypersurface in M. Okay. Of course, I'm being very, very casual here. So the technical lingo is, this is a space of all integral currents with no boundary with coefficients mod Z2. Okay, so this is a space which is well studied and well understood within geometric measure theory, but for the purpose of the next 30 minutes, it's no harm done if we just think of the space of all unoriented hypersurface with some appropriate topology. It's called the flat topology. So, and now on this space, you have a natural function, right? There's a natural function where you pick an element there, and you just compute its volume. Okay. Okay. So we have the space, we have a function, we look at the critical points, and the critical points, they are called minimal hypersurface, right? Critical points of F are called minimal hypersurface. Okay. So now we want to make sure that we have a space, we have a function. The question is, can we find critical points or not there? And a good picture to have is to imagine that my infinite dimensional space is something like this. So I can imagine that this is my functional f, it's just the height function, and that this is the space of all unoriented hypersurface on M, and that a good, or the toy case to understand how to find critical points is to just imagine we have a cylinder, we bend it, say we just assume this guy goes to infinity, and now we want to find critical points for this F functional, which I can think just being the height functional, right? So there's an obvious one, which is here, 0, like it's an absolute minimum. But on the other hand, I don't want to get, the minimal surface of area 0, the surface of area 0 is not a minimal surface. So I don't want to get this guy. I want to make sure I nail this critical point there, right? So the way we do this is following Moore's theory. You just pick some random curve there, okay? So let me do this while I do this here. So you want to apply Moore's theory, and the principle of Moore's theory is that the topology of the space will force the function to have critical points, right? So we want to use that. So let's just take, but let's do it a bit more general. So X is just some k-dimensional, topological space. And now I consider a function phi from this space into my infinite dimensional space. So this would amount, which is continuous, right? Okay. So the picture I drew here is when x is S1, in which case if this is S1, then what I'm doing is just considering a curve in the infinite dimensional space. But it doesn't have to be S1, it could be any topological space. And now, when I have this initial curve, I consider the homotopy class. I consider the set of all maps psi from X into there, which are homotopic to phi. Okay. So if I were to do a picture here, so a picture here would be, for instance, like if this guy is phi, or the image of phi, then psi would be something like this, right? Some homotopic map, psi. Okay. And now, so I consider my original map, I get a homotopy class, and then what I do is, for each element, I look at the guy of highest volume, which will be this point or this point, right? And then I do the min-max. So then I define L phi to be, for each element in the homotopy class, I maximize the volume. Okay. and then I minimize among all possible ones. So if I do this here, the best I can do, it's really this guy, right? Because each time I have a curve which is homotopic to that one, I must always go above this point. This is L. Okay. And this point is indeed the critical point of index 1, right? I have a direction which goes down, and every other direction should go up. Okay. So this is how we would try to find the critical point of a function which doesn't come from minimization. And this was indeed done by Pitts. This was Pitts' thesis. He was a student of Unburned, as I already said. And Pitts, what he showed is that assume the homotopy class is non-trivial. Okay? So this here is to prevent things like that, right? So I have to make sure that this is the homotopy class I'm considering and not something like this, right? Because if this is my original homotopy class, I can just shrink down and shrink it to a point. So I want to make sure that I'm not on this case and I'm on that case. Whether I'm in one case or the other, it's a statement about the topology of the space. It has nothing to do with the volume functional or minimal hypersurface, just a statement about topology. And you can write this way. Assume that the homotopy class is non-trivial. Okay? You cannot shrink it to 0. Then there exists sigma minimal hypersurface, which could have multiplicities. I mean, it could be the same guy with multiplicity 2. Such that the width equals the volume of the minimal surface. So for simplicity, let's just assume that the ambient dimension is between 7 and 3. The way I do this, it's because if I have that, then I don't need to say smooth outside a singular set of codimension 7. They are automatically smooth. Okay?
You still have Z2 coefficients?
That's right, yeah, that's right. I still have Z2 coefficients, but you still could have multiplicity. That's right, you know, that's a good, yeah, I'll mention that. That's right, yeah. If you minimize, you cannot, right? If you minimize, you cannot. But when you do min-max, it's not known. From the theory that is done, it doesn't follow. That's right. So, yeah, it would be great if, because I use Z2 coefficients, it's got multiplicity 1. But, you know, unfortunately, it's not known. The convergence in the theory is fairly weak. So the convergence is only done in the varifold sense, not in the current sense. So it's conceivable that the convergence in the varifold norm and the guy in flat topology in current sense is going to 0. So that is conceivable. So that's why, you know, it's not known. Yeah. Okay. So can I write here?
Okay.
So the philosophy of this, we call this Unburned Pit, Minimax theory. The philosophy is you find a non-trivial homotopy class, you get a minimal surface. Okay. So if I want to find infinitely many minimal surface, I should make sure I understand the topology of this space, right? Because I want to make sure this space has infinitely many non-trivial k-chains there, right? Okay. So we need to understand the topology of this space. Okay. Fortunately, this was done by Almgren. This was Almgren's thesis. His advisor was Federer. This was the problem that Federer gave him. The Almgren, he showed that this space is weakly homotopically equivalent to RP infinity. So technically speaking, what he showed was that the first fundamental group is non-zero, is Z2, and all the others fundamental groups vanish. And if we think about spaces which satisfy that property, the easiest one is RP infinity, right? The first fundamental group is Z2, and every other fundamental group vanishes, just like this space. Okay. So if they are weakly homotopically equivalent, Okay? In particular, we get that this, the singular cohomology of this space has to be the singular cohomology of this space, and we know the cohomology ring of this guy. So this will have only one, so the H1 in singular cohomology will have only one generator. We call that lambda, okay? And moreover, and now this is less rigorous, it's just like philosophically speaking, well, on RP infinity, I have, for every k, I have a k-dimensional projective plane, which is not homotopically trivial. Just take the flat k-dimensional projective plane. So I should expect to have, on that complicated space, also lots of k-dimensional projective planes, which are non-homotopically trivial. And just like RP infinity, this space should have many non-homotopically trivial, non-trivial, let me just write this way, non-trivial projective spaces. And of course, then we want to do min-max on these projective spaces, right? Because each time we find a cycle, we apply min-max theory, you get a critical point, right? Okay. So now we need to make sure we can find a representative for this k-dimensional projective space, because from the weak homotopic equivalence, that existence is just some abstract result. You know, we have to find the representative for that. Okay. So let me do that here. Okay. So let's do that with the definition. So I will define what should be a projective plane which is non-trivial in this infinite dimensional space, and then I'll make sure that we have lots of those. So let's just define this. So say you have some map phi from some space into, so these maps are all continuous. Okay. Now we say that phi is a k sweep out if, so I'll put the technical definition and the intuitively definition. So the rigorous way of stating is that if I pull back the generator of the cohomology ring of this infinite dimensional space, and I raise to the k power, I do the k product power, then I get something non-zero in singular cohomology of hk of x with coefficient z2. So this is, the technical definition. What this really means is incredibly geometric. So what this means is the following, is that given any k points in your n-bit manifold, there is an element here which passes through these k points. There is theta in x, so that these k points belong to phi of theta. Okay. So what this means is you give any two k points, there's a hypersurface in the image there which passes exactly through these k points. Okay. Okay. So now we want to do min-max among. So this is the algebraic topology definition of trying to make sense of what it should be. A non-trivial k-dimensional projective plane in that infinite dimensional space. Now, let's make sure that these guys exist, right? So let's give an example of something like that. Okay. So this example would be like, so take f some Morse function on m. Okay.
Can't read behind the screen. Yeah.
Okay. It's okay. Okay. Let me get the.
Should we put it on the screen?
It's okay. I'll just, it will fit in here. Okay. I'll make sure I don't write there. It's a Morse function. Okay. Now I want to consider a map from, let's go first by parts. So let's consider a map from K plus 1 dimensional Euclidean space into my space of all oriented hypersurface. And the way we can do this is I take K plus 1 points in R K plus 1. I index like A0 to AK. And then I do the following. I take the boundary. I consider this guy plus A1 f of x plus AK f of x k. I consider this less than 0. So I take k plus 1 points. Out of these k plus 1 points, I can make a polynomial on the variable f, which is A0, A1f plus A2f squared plus AKF to the k. And this gives me a function on M. Now I look at the set where that function is 0. Okay. And now, of course, I can notice that it doesn't matter if I take this specifically k plus 1 points or any multiple of it, because the 0 set is the same. So the map is not from Rk plus 1 into that space, but is only from Sk, the k sphere, into that space, because you can always, by scaling, the 0 set is not going to change, right? And now we also notice that if we change all points by its antipodal, then what's going to change is you change the sign there. It comes from negative to positive. But because I'm using Z2 coefficients, I don't care about the orientation of the set. The set is the same. It's just that the orientation changes. So because of this, this goes down to the equivalence relation, and that's exactly just RPK, right? So I get a map from RPK into this infinite dimensional space, and this map is a sweep out. Okay. So you can see that satisfies that condition. Okay. Okay. So now we have we have this notion of a sweep out, K sweep out. We know that they exist, so I want to do min-max there, right? Okay. And so to do this, we do the following. We define the K width of the manifold as being the infimum among all possible K sweep outs of the supremum of the volume of this. So what I'm doing is I'm doing the width among all possible K sweep outs. If we think about it, this is really the natural thing to do, because if we think how, for instance, if we think how the kth eigenvalue for the energy is defined, is also defined through a minimax, right? So let me just write this. So this mimics the following definition, that the kth eigenvalue for the eigenvalue, the kth eigenvalue for the Laplacian, okay? This is equal to, I minimize among all possible k plus 1 planes in W12, and then for each k plus 1 plane in W12, I maximize the Dirichlet energy or the Rayleigh quotient. I maximize the Rayleigh quotient. I should replace 0, right? So we know that for the Dirichlet energy, if I want to look at the kth eigenvalues, or make sure that I have an infinite number of eigenfunctions, which will be critical points, then we also do that to a min-max. So now we want to do the same thing for minimal hypersurface, that are critical points of a function. So I do exactly the same thing, where k plus 1 plane is replaced by k sweep out. But the definitions are analog. So Gromov, he calls this the kth nonlinear spectra of the manifold by comparison with that. Okay. And the crucial theorem here, this is the theorem that through Gromov in 87, but also Guth had an important contribution there in 07. And the theorem is that there exists some constant which only depends on the ambient manifold, so that the k width, they are less or equal than k over 1 n plus 1. So he estimates the growth of these k widths, or these nonlinear eigenvalues. Okay. So now we have all the ingredients in place. I'll just say what are the steps to prove the theorem. Let me now sketch the proof. Just say what are the key steps. So key steps of proof, not of this theorem, of that theorem there. Key steps of proof. Okay. So the first thing, okay. So what is the problem, right? The problem is that for each of these guys, I could apply the min-max theory and get it by minimal surface. Where could I get stuck? I could be always getting the same minimal surface, just with different multiplicities. So I think I'm getting different minimal surface, but I'm not. So this is the phenomenon we have to rule out, and that's why I need positive ricci there. Okay, so let me sketch that. So the first step to do is to make sure that if two of them, if omega k of m equals omega k plus 1 of m, so if any time this sequence, these k widths coincide, okay, so it should be, it's not hard to see that omega km is always less or equal than omega k plus 1, which is always less or equal than omega k plus 2, and so on, that the sequence is non-decreasing. Each time two of them coincide, we produce a lot of minimal embedded surface. So this is where we use the lucinic schnittman theory. So then if two of them coincide, there exists an infinite number of minimal embedded hypersurface. Okay. So let's just skip that. It's an argument where that's where you use this notion of coproducts, and the way you do this usually is called lucinic schnittman theory. So let's just assume that. And so if this happens, then I have infinitely many, so I might as well assume that my sequence is strictly increasing, right? Okay. So now in this case, I can apply min-max theory, and I get that each of these numbers can be written as some, let's put here, ak of some n ik volume of sigma ik. So each of these numbers you can realize by the volume of a minimal embedded hypersurface, but with multiplicities. With multiplicities, what it means is you can have, like, ak of them, which will have multiplicity 1, and then each will appear with some multiplicity which you put there, right? Okay. So we want to rule that out, So we want to make sure that all these guys will be distinct, right? Because it could be possible that I only have 3 of them, and then by linear combinations of positive integers, you just get all these numbers. So we want to exclude that. So the first remark is that we use Frankel's theorem So Frankel's theorem, it says that if I am on positive Ricci, any 2 minimal embedded hypersurface have to intersect. Okay, it's a beautiful argument just using a second variation of the shortest length geodesic. So in particular, I know that by the Minimax theory, I know that the support of all these guys, the union, has to be smooth and embedded, so they have to be disjoint. But from Frankel's theorem, any 2 minimal hypersurface intersect, so I can only have 1 of them. So this implies that this omega k of m is always some integer multiple, some positive integer multiple of some connected minimal hypersurface. Okay? And now the whole thing just becomes a counting argument, right? I have an increasing sequence of numbers, okay, each of which I realize by a multiple of some minimal embedded hypersurface. If I only had finitely many, okay, it's easy to see that if I only had finitely many minimal hypersurface, then because these numbers are strictly increasing, they can never repeat, right? And this is always positive integers of a finite number of them. You know, it's not hard to see by some basic counting argument that these numbers would grow at least like k, would grow more than k. Okay, would grow more than linearly. On the other hand, by the Gromov-Good theorem, I know they grow sublinearly. Okay, so a lot of them should have to repeat itself. So this contradicts the Gromov-Good theorem. If I didn't have positive Ricci, then it's possible that you could have, say, 3 or 4 of them which are irrationally related, and then just by integer combinations you expand all the numbers and they grow with this power. Okay. Okay, so in the, let's see, 5 minutes I have left, I'll just state some conjectures that Fernando and I have about this. Okay, it's just some open problems. Okay. Okay. Okay, so let me just state some open questions. So the first one, the motivation is the following. So I do believe that this number, that this k width, they should be able to say something about the ambient manifold. In the same way that the asymptotic behavior of eigenvalues also says something about the ambient manifold. So it would be nice, of course, to compute this on the 3-sphere. And just to compute on the 3-sphere, they are highly non-trivial. So the first are easy, right? So the first omega I, or the first I width of the 3-sphere with the round metric, this is just 4 pi. This is equivalent to say that the first eigenvalue of the sphere has multiplicity 4. It's the same statement. It's exactly the same statement. The first k nonlinear eigenvalue in the sphere has multiplicity 4. It shows up 4 times. Now, a student of mine, Charles, he can show that the 5th, the 6th, the 7th, and the 8th is 2 pi squared. In doing that, he has to use some of the work Fernando and I did to prove the Wilmer conjecture. Actually, it's a consequence of our proof of the Wilmer conjecture that the 5th, 6th, 7th, and 8th width of the 3-sphere is exactly 2 pi squared. Okay. Now, reasoning a bit more in topology, I guess the fact here is that the cup length of the space of all Clifford tori is 4 and not 5. And so it can show, Charles, it can show that omega 9 is strictly bigger than 2 pi squared. Okay. It has to be less or equal than 8 pi because we can just take the linear functions plus the quadratic homogeneous polynomials, and we can find a family which shows that this number is less or equal than 8 pi. So the question is, can this number be strictly less than 8 pi? If so, then I would conjecture that it has to be the Lawson genus 2 minimal surface, which is here. So the simplest minimal surface on the 3-sphere is the equator. The second simplest is the Clifford torus. The third simplest should be the Lawson genus 2 minimal surface. And Fernando and I, we found the variational characterization for the Clifford torus. So this would correspond to finding a variational characterization of the Lawson genus 2. And if we had this, I think one would be in good shape to try to prove the Wilmer conjecture for genus 2. So this would be the minimizer for the Wilmer energy in genus 2. So let me put now a ridiculously hard question, okay, which seems totally naive. And the question is that, does every n+1 sphere admits a minimal embedded hypersphere? Okay. So if the metric is the round one, there are examples due to Heixiang where he found lots of minimal embedded hyperspheres on the round n+1 sphere, which are not total geodesic. Of course, if it's a 3 sphere, you cannot, because it's a theorem of Unburned using some Hopf argument there. But the reason why this question is hard is that it's super difficult to estimate the topology. It's very hard to know when an n+1 dimensional guy is a sphere or not. If it's just for a surface, you just have to test pi1, right? It's incredibly hard. So this is, it's supposed to be. I have no idea how to do this. Another conjecture, it should be about the behavior of this K nonlinear width. So a lot of the conjectures Fernando and I have, they are motivated by the fact that these K nonlinear eigenvalues should resemble like the K linear eigenvalues of the usual Dirichlet energy. So it's a classical theorem of Uhlenbeck that for generic metrics, the eigenvalues of the Dirichlet energy are all simple, meaning they only appear with multiplicity 1. So we would expect the same thing to happen, that for bumpy metrics, each of these numbers can be realized by a minimal hypersurface with multiplicity 1 and index k. Okay. And so let me just finish with this one. So Gromma, keeping it in analogy that these numbers should behave like the linear eigenvalues. One, it's natural to ask whether there's a Weil law holds for them or not. And so Gromov, he conjectured that if we look at the growth of these numbers and we divide by k to the appropriate power, then this should be a constant just depending on the ambient dimension, not on the manifold, and then times the volume of the manifold up to appropriate scaling power. So this is like the Weil law for eigenvalues on a general manifold. Okay, so I have more conjecture, but I'll just stop here.
Thank you very much, André. Are there any questions?
And introducing more about the proof of this omega I, say for I equals 5, 6, 7, and 3.
Which one?
The estimates of omega I for I equals 5 to 8.
Yeah, that's right. How does that work?
Yeah.
Well, because so what you should you prove the so let's do omega 5, right? Okay. So for omega 5, you have a natural candidate, which is you look at the linear functions plus the falling harmonic homogeneous polynomial, which is x squared plus y squared minus z squared minus w squared. The nodal set of that is the Clifford torus, right? So you stick in the linear functions plus the homogeneous harmonic polynomial whose nodal set is the Clifford torus, okay? And that, now doing the same type of linear combinations here, you can get an RP5, right? Okay. And then what it does there, oh, okay, so wait. So what it does is the following. So if you pick that family, okay, you get that this number is going to be strictly less or equal than 2 pi squared, right? So you can check that. So now, of course, it could be 4 pi, okay? But what it does is the following. It picks the conformal family that Fernando and I used to prove this Wilmer conjecture, and that, of course, defines on a ball, and then he makes an equivalence class on the boundary of the ball to get it to be defined on an RP5, okay? And that family, and then he applies the theorem that I have with Fernando, which says that that family is not homotopic to the set of great spheres, okay? So in particular, the guy has to be strictly bigger than 4 pi. And then he shows that That's
It's actually
2 pi square. Okay. About that, yeah.
Go ahead.
Is there any good evidence for this Gromov's version of the Weil law for the plate widths?
No, besides geometric beauty, no, there's no. It's hard. Was there any evidence for the Weil law for the eigenvalues? For the compact well, for domains it's easy to prove, so I guess you could just do it by comparison. Yeah, so
I mean, Weil didn't sort of
that's right. Here it's hard. It's hard. Even on the tree sphere with round metric, it's hard to compute these numbers now. So I think Gromov's motivation was just these numbers should behave should have this syntactic behavior of k nonlinear eigenvalues. So I guess that's the only evidence you have. Yeah. Yeah. So fairly weak.
Any other questions?
So there's this famous relationship between length spectrum and spectrum of velocity. Can you give us some?
I would love to. Well, so so that relation, the guiding thing there is the Selbert trace formula, right? That's making the connection between conjugates and classes in the universal cover and then the length spectrum. Here, there's none. I would expect now. Of course, this is all conjecturally. I would expect that this minimal surface, they should be well approximated by the nodal set of a kth eigenfunction. So the only motivation we have there is the following. They are from a variational problem, and algebraic polynomials are great at solving variational problems, right? At least when things go to infinity, they tend to provide the best solution. But that would be the only connection I would expect. I would expect these guys to be approximated by the nodal set of some eigenfunction. But yeah, I would love that, of course. I would love to find a deeper connection between the length spectrum and these guys. Yeah, I would love that. Okay, yeah.
Are there any further questions?
Is it the Frankel's theorem, the only place you use the ricci?
That's right.
Ricci gradient.
That's right. Frankel is actually, when you prove the theorem, what you prove is, suppose you have an ambient manifold where every two minimal hypersurfaces intersect, then it must have an infinite number of them. And now, of course, if you have positive Ricci, we call that the Frankel property. Then they have the Frankel property. That's right.
Any more? Well, let's thank the speaker again.